there's a question which, we did at one point at the end of the lecture, and I really want to stress it. It's a very important type of question, okay? It involves a full cell, a oxidation half and a reduction half, okay? And we want to know if the potential, first of all, the potential of each electrode in the following cell, and indicate the reaction that would occur spontaneously if the cell were short-circuited. So to begin with, if they have a cell for you written like this and they said it's a galvanic cell, that means it is spontaneous. Also, if they have a cell like this and you have different concentrations than one, that means you're in non-standard state, and that means to get the overall potential of the cell, you must first correct the reduction potentials of each half, because I can't use the E naughts for UTM and the E naughts for FE. I need a corrected reduction potential, and then get the overall potential. At least that is one way, okay? So the first thing that we have to do, of course, is find what are the half reactions that are within this cell. So on the UTM side, I have, this should undergo what? The first part of the cell before the double line for the salt bridge. It's the oxidation half. Then they put the reduction half. That's how it is with cells. So the Fe2 plus, this part should undergo reduction. ولاحظين مش حاطينهم in the order that usually we like them written. يعني usually we write them in the order of how they are in the reaction. But they didn't do that. So if I want this Fe to be reduction, this part would be the oxidation half, okay? So إذا أنا لو بلشت هوني Fe2 plus goes to, if I just followed the order as written, Fe3 plus, I will see that I need one electron here. This is an electron loss. This is oxidation, and this is not what it should be. It should be a reduction. So I rewrite it, Fe plus one electron plus Fe, it goes to Fe2 plus, okay? The E naught is given. U, okay? So لنقول أنا بلشت U4. U4 plus goes to UO2 2 plus, because that's what I would have started with, if the cell was written properly. I would put plus, okay, U is balanced, plus 2 H2Os to balance the oxygens, plus 4H plus to balance the hydrogens. Let's look at the chart. 4 plus on this side, and this 4 plus on that side, 2 plus here. So I need plus 2 electrons on this end to balance the charges. What is this reaction now as written? It's oxidation. And do I want it in the form of oxidation? Yes, this is the oxidation half reaction. That is correct. Okay. So this is correct in terms of the reaction. Clear? Great. But when I write the reaction and I put the reduction potential for it, the reduction potential is always for what? For the reduction half reaction. But what is really taking place is indeed oxidation, and it should be, the reaction taking place is more like this one. Great. But let's write for a moment. So أنا real reaction هوني Fe3 plus 1 electron goes to Fe2 plus. These are the real two reactions taking place. For a moment, I want to write the overall reaction actually taking place. The overall reaction actually taking place is the addition of these two. يعني U4 plus 2H2O plus, بدي انتبه للإلكترونز. They must be balanced. I will multiply it by 2 to balance the electrons and remove them from the overall equation. Fe3 plus UO2 2 plus 4H plus 2Fe2 plus. That's the overall reaction. So we have the first way of solving the potential of the cell, of the overall cell, is to get first the corrected reduction potential for each reduction form of the cell. Low oxidation is taking place. So on the right-hand side where reduction is taking place, 0.071 is the E naught of Fe minus 0.0592. Always I look at the reduction half reaction. Products are reactants. إذا عندي plus sign, it's oxide red, or minus sign, it's the reduced form على الoxidized form. So Fe2 plus على Fe3 plus. You have these concentrations, you put them in, and you solve. Notice the reduction corrected potential is very close to the standard reduction potential. ما فارقة كتير. But يعني within the same range, 0.7 بعدنا 0.7 أمرار بتصير 0.8, but not overly different. We go to the deuterium. Even though oxidation is taking place, this is the reduction potential corrected. The E naught for the deuterium minus 0.0592 divided by 2 for the electron transferred on the deuterium half side. Minus sign يعني the reduced form على الoxidized form. UO2 is the oxidized form أكتر. So U4 2 plus على UO2 H plus to the power 4. This is in the reduction reaction. Okay. And this E is for the reduction. Solve, put everything in as numbers, solve, and you get a potential 0.12. Okay. It was 0.3. Quite a bit of a difference, and typically potentials that have H plus بقلبهم بتلاقوا and that they are affected a lot greater than those that do not. Okay. What happened with the difference in concentrations going back? Here we have a greater reduction potential with the different concentrations, meaning that indeed the reaction is more likely to undergo reduction, and the deuterium became smaller, less than what it was, which is even so it became more likely to undergo oxidation. The overall E of the cell is E of the reaction undergoing reduction on the right-hand side minus E of the reaction undergoing oxidation on the left-hand side. And this is nice, the idea of right and left, لأنه both are reduction potentials. Okay, reduction potential. All right, so we have E of the Fe minus the E of the yttrium corrected. We get an overall potential, which is positive. Are we clear on how to get the E of the cell from two corrected reduction potentials? Everybody, please. طيب. There's another way. And I don't know if I should not show you, but I think I should. And some of you would like to use it. I would have used it, definitely. If I have and I can find an overall reaction. يعني الأوكسيديشن عم نعمل له oxidation وبنكتبها بطريقة oxidation. Reduction, it's undergoing reduction and we write it in the reduction form. Okay? And we get an overall reaction. And we have the concentration of every single species in the cell, or sometimes they even give me the overall potential and I have to find the concentration of a species in the overall cell. So indeed, we have a reaction and this is it. And this is what we got by adding the reduction and the oxidation. That being the case, what I have is I can get the E of a reaction from the E node of the cell. We use Nerst minus 0.0592 divided by the number of electrons transferred in the overall reaction, log. If I use minus, it's products على reactants. If I use plus, it's reactants على products. Okay. So, as you wish in that, but the original Nernst is in minus. So products على reactants or Q. Okay, the Q, which is at any not necessarily at equilibrium, at any point in the reaction. Okay, so we have concentration UO2 2 plus, concentration Fe2 plus squared, concentration H plus to the power 4, U4 plus, and Fe3 plus squared. And guess what? E of the cell هي E naught reduction minus E naught oxidation. So I'm going to substitute. What's the original E naught of the reduction? Can it 0.771 if I recall? Minus 0.334. Notice these are the nodes, the original reduction potentials of the Fe and of the yttrium. Minus 0.0592 على total number of electrons for the two reactions to be added up, which is 2, log, and I substitute the concentration of every one of these species inside. يعني UO4 هي من هون دغري 0.2 UO2 هون 0.015 H plus هون 0.03 to the power 4. And I need the Fe concentrations from the page before. Can someone give me the Fe concentrations? Are you still with me?
Yes, doctor.
Okay. Right. Turn down. So the Fe concentrations and 0.01 and it must be squared, 0.025 and it's squared, and the concentration of H plus whatever it is. Okay. Solve, and indeed you will get the same exact overall potential. Amrar slightly different on the end, the last number, but you get the same thing. في أمرار أسئلة تجي they give you the potential يعني هني بيعطوكم هيدي الإي. Okay, they give it to you. And if that's the case and they're giving you the E, they can ask you for any concentration of any compound, okay, and to get that E value. And that's the case when it's much easier to use the overall Nerst for the overall equation instead of each half reaction reduction potential separately. Clear? Right? Right. I asked you, and please do this next one on your own. It's almost exactly the same, and use also the overall reaction. Don't forget always the H plus inside the overall reaction. Okay. Make sure you do it. Last time we did part 7, which was equilibrium constant K from E, and we derived that. Today we're going to just briefly continue a little bit with that part, okay? So we already derived that E naught of the cell is 0.0592 divided by N log K. Okay, or in terms في contesto log K هي NE divided by 0.0592. Okay, it depends on what you want. حفظوها بطريقة ما. أنا شخصيا حافظتها بطريقة اللوج K. Why? Because usually I need the K, so أنا حافظتها بطريقة log K equals N E naught divided by 0.0592. Why? Because I have the N, I have the E naught, I take divided by 0.592, and I get the antilog بسهولة. يعني whatever this number, it's the antilog 10 to the power of this. Okay, and that gives me the K automatically. Okay, so E naught is N 0.0592 log K. We have a reaction. They already gave you the reaction. And if you're already given the reaction, then you have you have already who's undergoing oxidation and who is undergoing reduction. So if I start with the Fe or the Ag, so Ag solid, هحط Ag solid. It goes to Ag plus, هحط Ag plus, and I balance the equation. So it's plus 1 electron. نرجع ل Fe. على الرياكتنت عندي Fe2 plus، على البرودكت عندي Fe solid. I need 2 electrons on this end to balance the equation. And to get the overall equation, we multiply the upper part by 2 and the lower part stays. And so the overall number of electrons transferred is 2. Now, do you really have to see who's undergoing reduction and oxidation? And yes. Do you have to split it like this? Not really. I can just go from the reaction and say Fe is going from 2 plus to 0. So definitely it's undergoing what? It's losing. It's gaining electrons. So it's the reduction. Ag is going from 0 to plus. So it's becoming more positive. That end is the oxidation. And number of electron transferred here, what's happening? It's reduction. I'm gaining 2 electrons. Here it's gaining 1 electron, but it's multiplied by 2. So I must have 2. So the number of electron transferred is 2. Okay, so E naught of the reaction or of a cell or of any reaction redox is E naught reduction minus E naught oxidation half. We are we are given here the E naughts reduction potentials. We get the overall. We can see that it is what? Not spontaneous as written. It may become spontaneous if I have maybe different concentrations, but as written, it is not spontaneous. Right? We use, if we want to find the equilibrium constant for this reaction, which is what we want, and that was the only question that they asked, what is the equilibrium constant? I had to do all this to get the E first, or E naught, sorry. دايما equilibrium constant, by the way, comes from the E naught of the cell, even if you have different concentrations. Because it's reached equilibrium, and when you reach equilibrium, you use E naught and not E. From the derivation, you would have seen that. Log K is N E naught divided by 0.0592, or 10 to the power of this. And we have the N, we have the E, and divided by this number, and you solve it, you get that the reaction is 10 to the minus 41.89, which is very, very limited. You might have to get it as an, make sure you know, again, the calculator, 1.28 times 10 to the minus 42. Very, very limited. In other words, there's really hardly any reaction between this Fe and this Ag. E naught is given for this overall reaction. What is the standard free energy and the equilibrium constant? Okay, log K or K reaction is 10 to the N E naught 0.0592. We're already given the E naught and we solve. Okay, we need to get what? The total number of electron transferred, because we're given E naught. So to get the total number of electron transferred, you could directly look at each of these. From Cl0 to Cl minus, we have a gain of 1 electron, but we must multiply it by 2 because there's a stoichiometry, or there is a 2 elements of Cl. So there's a net of 2 electrons gained. Let's look at the iodine. -1 becoming 0. There's a loss of 1 electron. So this is the oxidation. This is going to be the reduction. We're multiplying it as well by 2. So it's 2. So there is 2 electrons lost. So the number of electrons exchanged, gained, and lost is 2. So the overall N is 2. Of course, solve. Now, if you have to, and if this was not at 25 degrees Celsius, I want to on purpose put this, that you have to go back to the original form, which is ln K. Thus, K is E to the power NF E naught cell RT. Remember, it's the FRT that is the 0.0592 on the denominator end, okay? But here we're going back in case you ever have a temperature that is not 25 degrees Celsius. هلا بالمبدأ you know مش مطلوب بس you بالكورس بالمبدأ خلص معتمدين always 25 degrees Celsius بس دايما بالطب والصيدلة they might like to be extra annoying and have a temperature which is not. Delta G of the reaction. Delta G, we have already the E naught, so it's much easier. Then it's minus NF E naught. Again, if you've already memorized the equations, it becomes simple. N, again, is 2 electron transferred, which we needed to find. That's the F. And we have the E naught, 0.82. Again, the multiplication of this ends up giving you joules. Watch out for the units, depending on the answer. But this multiplication is joules overall. Joule per mole, which is a Coulomb mole. Joules volts, which is a Coulomb per mole, is the Faraday's constant units.